This is Srikanth S, Assistant Professor of Triple Department. In this session, I am discussing the topic in the subject of electrical elements of electrical and electronics engineering. In this, I am discussing the concept of alternating circuits. Now, let us go with the basic terms corresponding to alternating quantity. Here, alternating quantity is going to have both the magnitude and frequency. So, based on the magnitude parameters, we have uh, taken the average and RMS values. Now, the phase and phase difference, that is nothing but based on the where the waveform has started. Based on that, we are going to have some phase and phase angle difference. So first let us see what is phase. The phase is defined as the position of the waveform at a fraction of time period where the phase is expressed in an angle or radians. Here the phase is nothing but, here if you take a sine function, that is v of t can be written as Vm sine omega t. If it is started after some theta degrees. Okay, so the function can be written as V of t is equals to Vm sine omega t plus theta. And where this theta is nothing but phase. This is nothing but phase or phase angle or phase angle. And if the waveform is started before to this, then that will be taken as V of t is equals to Vm sine omega t minus theta. So this theta is nothing but the phase angle. What is the difference from the position of the waveform is called the phase angle or phase. And the next one is the phase difference. Phase difference is the difference between two waves is having the same frequency and refer to the same point in time. Same point in time. It is expressed in degrees or radians. Phase difference, the name itself says it is the phase angle difference between the two corresponding waveforms which is having same frequency and reference to the same point. That is nothing but when we are referencing between the same point, then that is called the phase difference. Then the phase angle difference is called phase difference. Here let us take the function of v of t as Vm sine omega t plus theta 1. Let us consider this as V1 of t. Next one is V2 of t is equals to, here Vm1 let us consider, here Vm2 sine omega t plus theta 2. So here the phase angle difference is nothing but phase angle difference or phase difference. Phase angle difference is nothing but, here we need to have, when we are comparing the two waveforms, the magnitudes should be positive or negative, and the function also should be either sine or cosine function. Then only we can compare the two waveforms. That is, if here Vm1 is also positive, Vm2 is also positive, and we are having sine function in both the functions, and here the phase angle difference is nothing but the difference between the phase angles, that is theta 1 minus theta 2. Theta 1 minus theta 2. And here it is the representation of phase, how we are going to see for a sine wave. Here the phase is defined as the fractional part of time period or cycle through which the quantity has advanced from the selected zero position of reference. Here this is another way of defining, but which shows the same representation, where phase is defined as the fractional part of the time period. That means it is a fractional part of the time period or cycle which the quantity has advanced. Here, if you take phase of plus Em value, phase of plus Em is pi by 2 radians. Phase of plus Em has taken a phase advancement of after pi by 2 time period only Em has reached, plus Em has reached. Or we can also take it as time period we are taking full as t, that is for quarter part the time period is t by 4 seconds. And in the same way phase of minus Em is 3 pi by 2 radians or 3t by 4 seconds. And this is the way how there are the different conditions when we are taking the two waveforms together, or when we are comparing the two waveforms together. Here the two waveforms together can be here when we are comparing the two waveforms, there are some conditions and some statements we are going to get. Here we are comparing the two waveforms corresponding to voltage and current, which are starting at the same point, and ending at the same point in both positive and negative half cycles, with the change in the magnitude, that is Im and Vm. Amplitude we are going to get as Im and Vm, and the function is following the same points. Which is starting at 0 and ending at pi in the positive half cycle, and in the negative half cycle it is starting at pi and ending at 2 pi. Then V can be represented as Vm sin omega t, I can be represented as Im sin omega t, and this we can write it as V at an angle 0 degrees, and this we can write it as I at an angle 0 degrees. So when we are having V at an angle 0, I at an angle 0, and what is the phase difference? The phase difference is theta 1 minus theta 2. Here theta 1 is 0, theta 2 is 0, so phase difference is 0. When the phase difference between the two waveforms is 0, then those two waveforms are called, they are said to be in phase. In phase is nothing but, if we draw the vector diagram or phasor diagram, both are on the same line. With change in the magnitude. Here if we draw the Vm here, Im is also on the same line, which is on the same line. So then we can say that this voltage and current phasors or waveforms are in phase. And the phase angle difference, when two alternating quantities of the same frequency have different zero points, when the two alternating quantities of the same frequency have different zero points, they are said to be they are said to have a phase difference. The angle between the 0 point is the angle of phase difference. The angle between the 0 points is the phase angle difference. Now we'll go with the second case, that is lagging. Here voltage waveform is starting at 0 point and current waveform is starting after 0 some 5 degrees delay. 5 degrees delay, which is starting the current waveform. When it is starting after 5 degrees, here V of t, voltage waveform, can be expressed as Vm sine omega t, and I can be represented as Im sine omega t minus phi. Im sine omega t minus phi. So here these waveforms, here we can write it as V at an angle 0 degrees. Here we can write it as I at an angle minus phi. I at an angle minus phi. So here I is starting later than the V. So we can say that current waveform is lagging behind the voltage. Current waveform is lagging behind the voltage by an angle of phi. The current waveform is lagging behind the voltage by phi angle, 5 degrees. Here, this is the current waveform, this is the voltage waveform. Here, the difference between the voltage and current waveform is 5 degrees. This is the lagging condition, that is when the waveform starts after the 0 point position. Then the other waveform which is starting after certain delay, that waveform is lagging with the reference waveform with that particular angle. And the next one is the leading. Here the current waveform is starting before the voltage, before the voltage, and this can be represented as V is Vm sine omega t. Before the voltage it is starting, so I can be represented as Im sine omega t plus phi. So here we can take it as this is the Vm phasor, that is V at an angle 0 degrees, and here it is I at an angle 5 degrees. Here Vm is the phasor with reference. This is the reference phasor we are considering, and Im is above the Vm. Im is above the Vm with an angle of 5 degrees. With an angle of 5 degrees. Then we can say that Im is leading. Im is leading Vm by 5 degrees. And in this we can also give the statement in such a way that Vm is lagging Im by 5 degrees. We can also give the statement like this. And in the previous case also, here Im is lagging Vm by 5. And we can also give a statement like this: Vm is leading Im by 5. This is the concept of leading and lagging. Now, let us go with the AC circuit with resistance, inductance, and capacitance. How we are going to get the impedance of the three elements, resistor, inductor, and capacitors, and how will be the voltage current phase relationships corresponding to these elements. Here we are considering, here is the resistor which is connected to a source of Vs, source of Vs, and here Vs is equals to Vm sine omega t, and across this Vs source resistance R is connected, and we are going to get the current I. So according to Ohm's law, I is equals to V by R. So I is equals to V by R, that is Vs by R, that is equals to Vm sine omega t by R. Here Vm by R we are considering it as Im sine omega t. Here we are not going to get any phase angle difference, omega t, omega t. There is no phase angle difference. So we can say that voltage and current for a particular resistance in AC, they are in phase. Voltage and current are in phase with the in phase to each other. So we can draw the waveforms such that with different magnitude, V is equals to Vm magnitude, I is equals to Vm by R magnitude, Vm by R magnitude. This is the I waveform. And here the voltage and current are in phase. Voltage and current are in phase. And here impedance is the concept of, it is the ratio of voltage phasor to the current phasor. That is nothing but V by I. Here is equals to V by I is equals to Vs by R. That is equals to R. So impedance of the resistor is that particular resistance itself. That particular resistance itself. Here, let us take the example corresponding to a pure resistor connected to a AC supply, and what are the parameters we need to calculate. So here an AC circuit consists of a pure resistance of 10 ohms and is connected to an AC supply of 230 volts, 50 Hz. Calculate the current, power consumed, and equations for voltage and current. So here, whatever the voltage which is given in any circuit, the voltage which is given is nothing but it is the RMS voltage. It is the RMS voltage. Until unless if the voltage function is specified, the maximum whatever the value which is given, that is nothing but the RMS value. So here first let us calculate what is the current. Current I is equals to V by R, that is equals to 230 by 10 ohms, that is equals to 23 amperes. This is the current. Power consumed, here there is no phase angle difference. So power consumed is equals to Vi, that is equals to voltage 230 and current is 23, that is equals to 230 into 23, we are going to get 5260 watts. This is the power value. And voltage Vm is equals to root 2 times the V, that is equals to root 2 into 30, because RMS value is nothing but Vrms is equals to Vm by root 2. In order to get the Vm value, we have to multiply Vrms with root 2. That is equals to, if we multiply with the Vrms with root 2, we are going to get 325.27 volts. And in the same way, Im is equals to root 2 into I, that is equals to 32.52. And angular velocity omega is equals to 2 pi f, that is equals to 100 pi. F is 50 hertz is given, 100 pi is nothing but 314 radians per second. So V of t can be written as Vm sine omega t. I of t can be written as Im sine omega t. So here V of t is equals to Vm value is 325.27 sine 314 t, and I of t is equals to 32.52 sine 314. This is corresponding to the pure resistance. Now we will go with the pure inductor. Here V of t we are considering it as Vm sine omega t, and here we need to calculate what is the I. And here V is equals to, or in an inductor, voltage current relationship is V is equals to L into di by dt. V is equals to L into di by dt. So here V is equals to L into di by dt. And what is the voltage we are giving? That is Vm sine omega t, that is equals to L into di by dt. L into di by dt. From this, we need I expression. We voltage expression we know. We need to calculate what is the I expression. So here I expression is nothing but, for getting I expression we are writing the di equation. Di is equals to Vm by L into sine omega t dt. So I is equals to Vm by L into integration sine omega t dt. So here Vm by omega L into integration of sine omega t is minus cos omega t. Integration of sine omega t is minus cos omega t. So this is the equation we got. But when we want to compare the two waveforms, we should have the same magnitude, that is either positive or negative magnitudes, as well as either sine or cosine function. So in order to get this cosine value, minus cosine value, negative cosine value in terms of sine, we are writing this value as minus cos omega t as sine omega t minus pi by 2. Sine omega t minus pi by 2. So which is equals to I is equals to Im sine omega t minus pi by 2, where Im is equals to Vm by omega L, where Im is equals to Vm by omega L. That here, if we take the impedance, Z is equals to V by I. Here V we can write it as V at an angle 0. I can be written as I at an angle minus 90. So V at an angle 0 by I at an angle minus 90. that is equals to V by omega L at an angle minus 90. This V will get cancelled. Omega L at an angle 90 degrees. That is Z is equals to J omega L. This is the impedance of the inductor. Z is equals to J omega L. And now we need to draw the waveforms, and we have to say that which waveform is in lagging and which waveform is leading. Here we got omega t minus pi by 2. Minus pi by 2 is nothing but the waveform is starting after the 0 point. After the 0 point. That is, if we consider V phase is at 0 point, I phase will be exactly 90 degrees displacement from the 0 position, and it is starting at 90 degrees and it will end the positive half cycle at 270 degrees, and then again it will continue the negative half cycle. So here we can say that the current waveform, yeah, we can say that here we can say that the current waveform is lagging behind the voltage by pi by 2 radians or 90 degrees. Pi by 2 radians or 90 degrees. Here, this is the voltage with the reference, and this is the current phasor with exactly 90 degrees. So here, I is lagging or lags the voltage by 90 degrees. I is, sorry, V is leads I by 90 degrees. These are the two statements we can write in terms of lagging and leading concept. Now let us go with the problem. A pure inductive coil allows a current of 10 amperes to flow from a 230 volts 50 hertz supply. Find inductance of the coil and power absorbed and equations for voltage and current. Here we need to calculate based on the voltage and current which is given. We have to calculate the inductance value. So here XL inductance value is equals to V by I, that is equals to 230 by 10, that is 23 ohms. Now we got the XL value as 2 pi FL, that is omega L, where L is equals to XL by 2 pi F. XL by 2 pi F. Here the frequency value is given 50 Hz. If we substitute, you will get the inductance value as 0.073 Henry. And here it is a pure inductance. For a pure inductance, there is no power absorption. There is no power absorption. And we need to calculate the maximum value of voltage and maximum value of current, that is equals to Vm is equals to root 2 into V, that is 325.27, and Im is equals to root 2 into I, that is 14.14 amperes. Here by omega L we have to do, okay, sorry, here already I value is given, that is 10 amperes. Root 2 is we are going to get I is equals to 14.14, and omega is given as 2 pi F, that is 314 radians per second. So V is equals to 325.25 sine 314t, and I is equals to 14.14 sine 314t minus pi by 2. This is the way we have to calculate the parameters corresponding to pure inductance. Now we will go with the AC circuit with a pure capacitance. Here for a capacitor, voltage V is given as, this is the sine voltage V of t function which is applied across the capacitor, that is Vm sine omega t. And now we need to calculate, now we need to calculate what is the current waveform. What is the current waveform? So for that we are taking the charge equation. Charge Q is equals to CV. From this, Q is equals to C Vm sine omega t, where I is equals to dq by dt. I is equals to dq by dt. If we differentiate this equation with respect to dt, we are going to get I is equals to C into Vm differentiation of sine omega t with respect to dt. Differentiation of sine omega t with respect to dt here. So we are going to get omega into cos omega t. Omega into cos omega t. So while comparing the two waveforms, we need either sine functions or cosine functions. So for that, we are converting this cos omega t into sine omega t, that is sine omega t plus pi by 2, sine omega t plus pi by 2, where I is equals to Im sine omega t plus pi by 2, where here Im is equals to omega c Vm. So here plus pi by 2 is nothing but the waveform for current has started before the 0 point. Before the 0 point it is started, and this difference is pi by 2 difference. So here we can say that current waveform is leading the voltage by 90 degrees. Current waveform is leading the voltage by 90 degrees. Here this is the phasor representation of voltage and current across the capacitor. This is the V and this is the I, exactly 90 degrees displacement. So here we are going to get the leading and lagging concept. Here the current is leads the voltage by 90 degrees and voltage lags current by 90 degrees. And now we need to derive the value of impedance, that is V at an angle 0, and here we are writing I at an angle 90. So Z is equals to V by I, that is equals to V value V by V by omega C V, omega C Vm at an angle 90, that is equals to minus 90 degrees by omega c, that is equals to minus 90 is nothing but j by omega c, that is equals to j by omega c, that we can write it as minus j into xc, where xc is equals to 1 by omega c. This is the capacitance of the, sorry, impedance of the capacitor. Now in the same way we are going to calculate the capacitive reactance, RMS value, and equations for voltage and current. Here, a 318 microfarad capacitor is connected across a 230 volts 50 hertz system. Find the capacitive reactance. Find the capacitive reactance, RMS value of current, and equations for voltage and current. Here, capacitive reactance we have taken already XC. We got it as 1 by omega C. That is equals to XC is equals to 1 by 2 pi FC. That is equals to 10 ohms. If we substitute the frequency and capacitance value, we are going to get the value as 10 ohms. And I is equals to V by XC. Here V value is 230 volts by 10, that is equals to 23 amperes. And here Vm value is root 2 into V, that is 325.27. And Im value is root 2 into I, that is equals to 32.53 amperes. And here we got the omega value as 2 pi f, that is equals to 314 radians per second. And now we are going to write V of t and I of t functions, where V of t is 325.25 sine 3140 and I of t is 332.53 sine 3140 plus pi by 2. And here the current is leading the voltage by 90 degrees. Now let us go with the series combination of elements, that is RL series circuit, RC series circuit and RLC series circuit. Here from the phasor diagram, here this is the VR and VL, voltage across the inductor, and this is the voltage across the resistor. Here if we draw the phasor diagram, voltage across the resistor will be in phase with the current. Voltage across the inductor will be 90 degrees leading. Voltage will be leading, current will be lagging. Here the voltage across the inductor, we are taking it as leading voltage. Now the resultant voltage will be, this is the resultant voltage V, and with a phase angle of 5 degrees. With a phase angle of 5 degrees. Here V is equals to square root of VR square plus VL square, where VR is equals to I into R, where VL is equals to I into XL. So V is equals to square root of I into R square, I into R whole square plus I into XL whole square, where V is equals to I into square root of R square plus XL square, where V is equals to IZ, where impedance Z is equals to square root of R square plus XL square, R square plus XL square. So here we can write it as, in terms of imaginary value, I is equals to R plus J XL. This is the impedance of the RL series circuit. And here the phase angle can be taken as, phi is equals to, which is from the, how we are going to get the phi value, that is tan phi is equals to VL by VR, VL by VR. So from this, phi is equals to tan inverse of VL by VR, where VL can be written as I into XL by IR, where I into XL, II both are same because they are connected in series. So XL by R, that is equals to omega tan inverse of omega L by R. So from this, average power is equals to, generally power equation is in the DC circuits only VI, whereas in AC circuits VI will multiply with power factor, that is cosine value of phase angle difference between the voltage and current. That is power is equals to VI cos phi, where cos phi is called power factor. Cos phi is called the power factor. And this is the way we are going to draw the impedance triangle. Here V is equals to IZ. Here VR is equals to I into R. VL is equals to I into XL. The resultant voltage V is equals to I into Z. This is Z or XL. Where impedance Z is equals to square root of R square by XL square. And power factor is equals to cos phi is equals to R by Z. Cos phi is nothing but adjacent by opposite, R by Z. And phase angle is equals to tan inverse of XL by R. Here the current leads or lags behind the voltage. That is, here current will be lagging the inductance voltage by 90 degrees. This is corresponding to RL series circuit. Now we'll go with the RC series circuit. Before going to the RC series circuit, let us have one problem on RL series circuit. A coil having a resistance of 7 ohms and an inductance of 31.8 millihenry is connected to a 230 volts 50 hertz supply, and we need to calculate the circuit current, phase angle, power factor and power consumed. So here, in order to get all these values, first let us calculate the impedance value. So for calculating impedance, first let us calculate XL value, reactance of the inductor, that is equals to 2 pi FL, that is 2 into 3.14 into frequency is given as 50 Hz into 31.8 into 10 to the power of minus 3, which is equals to 10 ohms, where Z is equals to square root of R square plus XL square, which is equals to 7 square plus 10 square, where we are going to get it as 12.2 ohms, where current is equals to V by Z, that is equals to the voltage, RMS value of voltage is given as 230 volts. Current I is equals to V by Z, that is equals to 230 by 12.2, that is equals to 18.85 amperes, and phi is equals to tan inverse of XL by R, that is equals to tan inverse 10 by 7, that is equals to 55 degrees lagging, and power factor is equals to cos phi, that is equals to cos of 55 degrees, that is equals to 0.573 lagging, and power is equals to, if we substitute Vi cos phi, the power is nothing but, in AC circuits power equation is Vi cos phi. So the power P is equals to Vi cos phi. Power P is equals to voltage current multiplied with the power factor, that is Vi cos phi, which is equals to 230 into current value we got it as 18.85 into power factor we got it as 0.573, that is equals to 2484.24 watts. This is the way we need to calculate the parameters corresponding to RL series circuit. Yeah, in this session we have discussed the voltage and current relationships for pure resistor, pure capacitor and pure inductor, and the voltage current relationship for RL series circuit. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.